All right, so let's continue on here. So those are the three factors we just identified that affect our flow or our resistance to flow. The radius of the vessel, right? So how wide is that vessel, or the lumen of that vessel rather? And that is determined by how large the radius is. We know in arterioles and small arteries, they have the ability to regulate their size. And we saw this last semester, right? The smooth muscle that lines arteries has this ability to basically vasoconstrict and vasodilate, to change its radius or to change its size, and that will affect the flow. We know that the length of the vessel affects the flow. In our pulmonary circuit, blood is basically moving from heart to lungs back to heart, okay? A very short distance to travel. And in the systemic circuit, blood is moving all the way from your heart out to the tips of fingers, down to the tips of toes, to the scalp. And so the vessels have a much further or longer distance to travel. And that's why we have so much more resistance in our systemic circulation than we see in the pulmonary circulation. Okay. Mm-hmm.
There was a note on the previous slide.
This one? Okay, so this is just pointing out that the pulmonary circuit has much less resistance than the systemic circuit does, okay? And we just sort of described why, right? That short distance that the pulmonary circuit has to travel versus the long distance that we see in the systemic circuit. Okay, so going back to our factors here, we talked about the length, and then the third factor that we want to consider is the viscosity. Now, the viscosity is the thickness of the blood, and this makes sense, right? If we have blood that basically has more solutes dissolved in it, or has more red blood cells, it's going to be much more sluggish to travel, and that is going to decrease the flow, okay? That's going to be more of a resistance to that flow of blood. And we can see the opposite in things like anemia. If we have decreased red blood cells, we're going to have less resistance because we have decreased viscosity. Okay, so viscosity, length, and radius are the three important factors. So radius is going to be this aspect, right? How big is the lumen? Viscosity is going to be how thick is the fluid, and length is going to be how long is that vessel. These three things determine resistance. All right, let's look at two scenarios here. So we have two containers, one on the left, one on the right, and we have two tubes or two vessels that are connecting both containers. We have a pressure gradient, which we sort of mentioned before, of 40 millimeters of mercury. And so we have flow. We know that we have flow because we have a pressure gradient. So water or blood is going to want to move from side A, or the left side, sorry, to the right side. And it can do so through conduit A or through conduit B, okay? Now, we see a higher rate of flow in A. Why do we see a higher rate here? Sorry? Less resistance. And why do we have less resistance? Because it's bigger. Specifically, what factor does this tie into? The radius. Perfect. So we have a bigger radius, translates to a greater diameter or greater lumen, which is less resistance, okay? So we have greater flow. Alternatively, in the conduit at the bottom, we have a decreased radius, so we have more resistance and we have a less flow. So who can describe the relationship between radius and flow? So as the radius gets smaller, what does the flow do? Also gets smaller. So is that inverse? Directly proportional, right? So that's a directly proportional relationship. As the radius gets smaller, so does the flow, right? Radius decreases, flow decreases. Who can describe the relationship between the radius and the resistance? Inverse, right? So what happens as the radius gets smaller? The resistance increases. So as the radius gets smaller, the resistance increases, and that's going to translate to what type of flow? Less flow, good. So radius gets smaller, resistance increases, flow decreases. So resistance and radius have a inversely proportional relationship, and radius and flow have a directly proportional relationship, okay? All right. Any questions on that? Any questions? Any questions? Okay. I hope you're not completely fried. We're going to do some more math, okay? Okay, so when we speak about resistance, we use a physical law called Presailles law. And this law is how we define or quantify resistance, okay? Now we're going to describe what resistance is first, and then we'll look at the actual formula. So based upon what we just said, and based upon this law, resistance is equal to 8, and this is a standard number, right? So this is a fixed number, 8, multiplied by the viscosity, right? That's the viscosity of the blood or the liquid, multiplied by the length of the vessel. And that's going to be divided by pi, which is another fixed variable or standard, multiplied by the internal radius of that vessel. And that's going to be raised to the power of 4, okay? So resistance is equal to 8 times the viscosity times the length of the vessel divided by pi times the radius raised to the power of 4. Ready? And to simplify this, we can say that resistance is equal to 8 eta, which is the Greek symbol that represents viscosity, L, which is our length, divided by pi r to the 4th, okay, or pi r4. And we mentioned an equation that had resistance in it before. Who remembers that equation? That equation for bulk flow. Who remembers that equation? Right, so we said flow or bulk flow is equal to our pressure gradient divided by R. So we can simply just plug this equation in for R, can't we? Yeah, we could. So as a result, bulk flow is equal to pressure gradient divided by R. Well, we won't put R, we'll put this formula, which is 8 eta L divided by pi r to the 4th. And because this isn't good math, we're going to rearrange this equation to be delta P times pi r to the 4 divided by 8 eta L, okay? And this is a more detailed equation for bulk flow, okay? And what this equation really tells us is some important relationships between each of these variables and our bulk flow. Relationships that we just sort of described, right? We remember describing that the pressure gradient is directly proportional to bulk flow, right? Also, that the radius is directly proportional to bulk flow. We also said that viscosity is inversely proportional to bulk flow, and that length is inversely proportional to bulk flow, okay? And I'll give some examples of practically looking at that, at those those relationships, but I really want you to look at this formula and see how we can derive those relationships. So bulk flow is directly proportional to pressure gradient, directly proportional to radius, but inversely proportional to viscosity, which is represented by eta here, and inversely proportional to length, okay? So let's write that out down here, and then we'll talk a little bit more about it. So directly proportional to delta P and to our radius. But inversely proportional to eta, which is our viscosity, and length, which is L, okay? And so what does that mean? What does that mean? What do these relationships mean practically? Let's take this, for example. Bulk flow inversely proportional to eta, or to viscosity. What does that mean for us? Exactly. The smaller eta gets, the bigger bulk flow gets. And in a more practical application, right, the less viscosity we have, the more flow we have. The thinner our blood is, or the thinner a liquid is, the more easily it will flow from one place to the other, okay? What about the length? We kind of talked about the length already. So this is an inverse proportional relationship as well. So as the length gets longer, the flow gets smaller. And we talked about why, right? There's more resistance. So if we increase the length, if we have a longer vessel, think about your femoral vessel versus, say, your pulmonary vessel, right? You're gonna have more resistance, you're gonna have less flow in a longer vessel than you will in a shorter vessel, okay? Let's look at these directionally proportional relationships. So as we increase the pressure gradient, we're gonna have more flow, and that makes sense, right? We have a bigger force. If we have a bigger differential, we have a bigger force, and that's a bigger driving force that moves blood from one area to the other. Likewise, which we mentioned before, if we have a bigger radius, we have a bigger vessel, we have a bigger flow, okay?